All right, so let's look at Chapter 7 of your Astronomy Coach by me, Celestia. It's our solar system, our hood. It's the only place in the universe we can send robotic probes to, or people you don't like, out to those planets, moons, and investigate them. We can't get to the nearest star, not in reasonable time. So it's our hood. It's a place we can really investigate, get our hands on stuff rather than look at it. So what do I do in that chapter? In chapter 7, section 1, thank you, we talk about universe, galaxy, solar system. We're reviewing chapter 0, just that context. What is a solar system? In 7.2, we talk about the clues. What clues? What's happening right now? What do we know right now that tells us what must have happened? In 7.3 so through 7.5, we talk about the creation or formation of our solar system, something I'm going to talk about right now. And in 7.6, we talk about the contents of our solar system in order. Not going to do that on this video. 7.7, 7.8, memory aids that I've created for sizes and distances of the planets. And so you can look in the book for that. While we're doing this, we get a glimpse at how stars and planets are formed. This is the one star, our star, sun, that we're going to look at in this example, and our planets, our hood. But there are other stars, and they likely formed in a similar fashion. So we'll get a sense. This is an introductory course. There are a lot of details in here that people are still working on. So let's take a look here real quick and get a context. What is a solar system? So let's go here. Let's see, a galaxy, the universe. What's the difference? Solar system. So here we are on Earth. We look out through this spherical window we call the celestial sphere, and things are out there in the universe. What do we find? You know, initially people could only see what their eyes could see, and they thought that was it. That's all that existed, little dots in the sky. What were those things? But now we know, we look out into the universe. The universe is our word for everything, unless there's multiple universes. And in the universe, there are about 100 billion galaxies still being explored. So there are galaxies upon galaxies in this universe. We know the universe started about 14 billion years ago, right? And it started in the Big Bang and expansion out of nothing into nothing. Some crazy stuff from chapter 0, right? So the universe. And as the universe formed, it started to bunch up into clouds. And those clouds were enormous on human scale. And those clouds became galaxies. And so inside the universe, we got maybe 100 billion galaxies. We got some small galaxies, some big galaxies. You know, maybe 10 billion stars, maybe 100 billion stars. That's a pretty big galaxy. Maybe 1,000 billion or trillion stars. Right? So within this galaxy, we've got stars and stars and stars. Each star, maybe around each has planets. Maybe there's moons. Maybe there's life. We're about halfway out in our solar system. This is our Milky Way galaxy model, which is wrong. Recent evidence, I love it because it's wrong. Really, there's a barred spiral, so we got a bar of stars, and that's fairly recent evidence. So we're exploring. We're in the process of exploring. From here, from one star, one planet, around one star. Where are we in the universe? We're in one galaxy, a good-sized galaxy, Milky Way. We've got another big galaxy nearby, the Andromeda galaxy, also big. And some other small, about 30 small ones around us. And then there's galaxies upon galaxies. So we're talking about our hood, though. This isn't really our hood. We can't even get to the next star. We're one star and the little chunks that formed around it. How did that happen? Okay. Notice it's a disk. We'll talk about that in just a second. So here we have our hood, our solar system. We know it's not geocentric anymore. It's heliocentric. That is, we got a bunch of stuff going around this thing we call sun. It is Helios, our star, and all these chunks. We got planets, we got moons, we got things like that, dust and debris. So how did that form? All right, cool. Let's just tell a little simple story, give you a sense of it, and you can go deeper if you like and look at some cutting edge things. So, talking about clues, 7.2. Read up on that in the book, in your astronomy coach. But there are some clues, some telltale signs here. I mean, the planets aren't going around sun in all these different ways. They're all going this way, right? Planets are going this way. They're all going the same way. No one's driving the wrong way on the freeway, right? And as they go this way, they're also spinning this way with some variations, which we talk about. There are always these exceptions, but they're basically spinning this way. So these guys spinning around and going on the same level, the same plane. Orbiting, spinning, with many of the moons, most of the moons going in the same direction, the planet is spinning. So we've got all this motion going on here. So that's a big clue, right? Other clues, we find a lot of metal rock in here, and lighter weight stuff way far out, called differentiation. We're going to talk about that stuff. So you just see that. You see that to be true, that there's a lot of hydrogen and helium and ammonia and methane and water out there in the farther, and a lot of rock and metal in here. So there's a variety of clues that we have. The planets have swept up their paths. That is, there's nothing there. There are things there, but it's pretty clean room, right? That's accretion. We'll talk about that in a second. So we see these clues. Another big clue that I talk about in the coach, electrons love protons, okay? So electrons love protons. And what does that mean? If an electron flies by a proton too fast, it'll just won't connect. But if it flies by a proton slow enough, they're going to get married. And that is what hydrogen is. The universe initially started in this Big Bang, whatever that is, as best our evidence says right now, and mostly hydrogen, some helium. How do you get helium? Well, we'll get into that a little bit more. But protons hate each other. Protons hate protons. So if they're flying along, they see each other, they go, whoa, they push away through the electric force. They fly along faster, they get closer, and they push away even stronger. So what chance have they got to bond? I mean, they hate each other. But if they get close enough, if you squeeze them, they're going fast enough, hot enough, they get in there, and all of a sudden they get really close and they fuse. They love each other through the strong force. So there's another force which is critical for stars shining, and that makes atoms. Protons and neutrons form the center of everything around you, this stuff. And then there's electrons, which they love protons, so they're always hanging around like groupies in a rock band. So there they are. But how do you get those protons close enough to fall in love? Well, it has to do with stars, okay? And so here we are. We've got carbon, which has 6 protons. We've got some oxygen, which has 8 protons. Oxy, octopus, octagon, 8, right? We've got nitrogen there with 7 protons. We've got iron, 26. We've got silver and gold, lots of protons in there. How do you get those things to squeeze together? So let's take a look. I mean, really, if we take a look at a simple story here, we can imagine that our hood was just a gas cloud, a small gas cloud in a small region of our huge galaxy. A gas cloud of mostly hydrogen, some helium gas. But if it's only hydrogen and helium, you can't make us, you can't make skin, you can't make blood, you can't make trees. And so with that gas, you had to add some stuff, like carbon, oxygen, nitrogen, and some stuff for jewelry. So there must have been nearby in our galaxy, very close by, a large star. I've named it Big Mama, because really that's our mother. And that big star, large stars, are able to, through gravity, squeeze together these protons and make them fall in love and build up bigger atoms. Now the thing about big stars is they live fast and die young. And so while we're just kind of slowly coming together, Big Mama's going, and it blows in a supernova. So reasonable explanation. No one's got a picture back there, but this is like, okay, how can we get those atoms? So perhaps a large star, which I've named, taken the liberty to name, added big atoms to our hood. So there's one early part, like, hey, big stars live fast, die young, and provide the atoms that we need to create life. Great. So let's look at our hood, our solar system. So here's what we got now, a gas cloud with added atoms in here. we've got gravity pulling in, it's spinning. You know, this thing blows, you got a gas cloud, things pull together, they tend to be off center, they spin, you got a gas cloud spinning and pulling in. When was this? Like, 4 or 5 billion years ago, 4.6 billion years ago, somewhere, right, as it starts to form, And what happens when you're spinning and you pull in? So I'm not going to do this on this video, I don't want you to do this, I do it in class. But what I want you to do is take something. Now, this is more dramatic if you take something heavy. Something massive here. Spin on a chair or something, watch out, clear your path. Oh, that would hit, so that'll hurt. But as you spin, pull in. Think about a dancer, think about an athlete of any sort. When they tuck or pull in as they spin faster. Now that's hard to do because this guy wants to go, Newton's first law, right? These things tend to go in just a straight line. They'll go in a straight line, right? So I got to pull them in, and to pull them in even more, it's harder. So to speed up, you can get tired. You have to pull in. But the interesting thing is that if you are spinning and you do it this way, it's not such a problem. I mean, these want to fly out that way, but now I'm spinning here, and this is easy to fall in here. And in fact, if you're spinning and you do this, you won't speed up. So it didn't take much effort. It takes effort to speed up. So what happens is, as this gas cloud pulls in, it pulls in easily this way. Let me just show you one little demonstration of this. And so, the other clue is rotational physics. We play around in the laboratory and we see how fast and what's it take to make something spin faster or slower. I mean, if I go like this, if I rotate something, what does it want to do? See these guys? They want to go out. Things are going to spin out, so it's hard to pull them in this way, right? It's hard to pull it in this way, but it's easy to pull in this way. Let me show you. This is a rotator, lots of rotations in here, so rotational physics is a big part of understanding this sort of thing. It's kind of like a rotating cloud, right? You see that? Look at the pulls. What happens, gravity pulls in, spins up faster and faster. As it spins faster and faster, harder to pull it in this way, but easy to pull in this way. And our sphere quickly becomes compressed into a disk. And so in space, gravity pulls from all sides, and we have lots of spheres in space. If they're solid, they'll stop, but if they're gaseous or flexible, they turn into disks. We have disks and spheres in space. Okay, so let's finish the story up here. We're just about done. Water. Elements of life. All right, so here's the story. Right, Big Mama's out there living fast, dying young, fusing atoms. She blows supernova, adds some good stuff to our hood. Our hood's pulling in by gravity and spinning, pulling in, spinning faster and faster, falling in, creating a disk. And what's at the center? Most of the gas is at the center, which is becoming a star, or becoming our sun. We call it a proto-star, which we are going to name Sun or Helios. So most of the gas by far went here. And we're spinning around, so we got this gas cloud going here. So what happens? 3 terms are good to think of. So let's go over here. Remember these 3 terms. And that's a good introduction to how a star forms and planets form. Condensation, differentiation, accretion. Maybe you'll find a memory aid, CDA, whatever that means. You can come up with one. What is condensation? Well, vapor, water vapor, steam, when it cools down, the water vapor joins together and you get drops of water. In space, gas bits come together and they go right to solid. So they get little solid, tiny grains. Okay, so condensation, things, kind of the gas cloud condensing into solid bits. Okay, that's all that is. And these can happen, you know, simultaneously, whatever order, but you can think of it this way. So we got our spinning disk, most of the gas at the center, our star. So as that proto-sun in formation gets hot and glows and tends to glow, it tends to blow things out. Remember the solar wind, light, and push low mass atoms farther out. The more dense stuff is a little harder to push out. We got atoms and molecules that are more massive, metals and rocks, which stay in close. Okay, so then we get differentiation. Remember, we got sun, then we got metal, rock, and then we got more lightweight stuff. That's what differentiation is. It's much like Earth, where the more dense stuff, namely iron, sank to the middle. Then we got rock, like that. So planetary differentiation. This is solar system differentiation. Different levels. And we're almost done. The accretion. So accretion, you can think of the word accumulate or accrue, or just think sweep up and grow. So we've got this disk, we've got most of the sun, or becoming sun, most of the gas right here, and we've got this disk spinning around of stuff. It's a pretty messy place, but then they start chunking up. You start getting chunks, and they run into each other, and they might make a bigger chunk, and then this one runs into that one and might make a bigger chunk. Now in reality, there are some real issues here, like how does a baseball join up with a basketball? I mean, are they going to stick? I mean, two rocks that size? Are they going to hit, pulverize, and then come together? That's interesting, right? But some of those questions are still being explored. How does something that size sweep each other up, grow, join together, and grow? But nonetheless, we talk about accretion, sweeping up and growing, and so this guy is going to go over here and pick up that guy. Now we got something bigger. Then it's going to come over and pick up this guy, and they're going to go around and whatever, some messy process. And all of a sudden, it's going to be less messy. And these planets are going to sweep up their paths and grow and clear their room, clear their pathway. Accretion. We have an accretion disk. Okay. So accumulate, sweep up, and grow. So that's kind of a simple picture. Gives you a sense of how our cloud turned into a disk. The gas condensed into solid bits. We had differentiation because the center was our proto-sun, blowing things out. Sun started to blow things out. We get more low-mass things getting blown out. Accretion, accumulating. Some real questions in there. And finally, in the last bit, we've got this nice cleaned up kind of solar system with planets and moons and leftovers. We have this period of heavy bombardment, so it was still messy. And now we just got some big chunks running around. So our hood was a messy place. Lots of collisions. Let's see, that's 4.5, 5, I think, whatever. 4.5, 4.6 billion years ago, right? That this is forming. And then in the first billion years, it was still pretty messy. Now really, there's an early period of heavy bombardment and a late period. So you can explore that and read about that if you like. And it's important details, but I don't want to overwhelm as an introduction. So lots of collisions. As things collide, they kind of join, clean up, less things running around the streets of our hood. Cleaned up, fewer collisions. And what we find is that worlds that have cooled, probably because they're small, but they've cooled, they still show their scars. They haven't changed much. Tectonics, volcanism, not much of that. And so we still see heavily cratered surfaces. If you see a heavily cratered surface, you go, hey, that hasn't changed much because the cratering stopped. All the craziness, the riot stopped, right? Worlds that have changed show fewer craters. And so that tells us too, it's like, hey, there's not that many craters here. I see the volcanism, but there's not as many craters, so it must have slowed down. We can check that out. Okay, and finally, hot item, latest idea. People are exploring not only our solar system, but looking at other solar systems and that's a tricky business. You can't really see the planets. But there's a model. It's a very nice model. Actually, it's called the Nice model, after the city in France where it was kind of thought about. And that Nice model introduces some interesting ideas. They're kind of subtle, but the basic idea here is planetary migration, meaning some big boys might have moved, changed places or changed location and shifted accordingly. We look at different things, the Kuiper belt objects and things like that to think about that. So this isn't a done deal, but it does give you a nice sense of how a star and the little bits around it might have formed. And by the way, maybe one of those little bits, or maybe more than one, had life, has life on it, or had life form on it. And we know now, too, that life forms out of carbon-based, nitrogen, oxygen, carbon-based organic molecules that are not living. You collide them, and you can create amino acids, the building blocks of life. So collisions, a violent place, may be the birth of life on some of these worlds. This is what we're going to study is our solar system. By studying our hood, we can imagine or think about or explore other ones, but we can't go to the other ones. This hood, we can send robotic probes to, thanks to our engineers, scientists, and everybody else. Okay, cool. So read up on the rest of that chapter and get to know your hood.